All right, now we are on to part 6. What can we use the climate projections for? We've talked all about scenarios, we've talked about climate models, we've talked about uncertainties, but what can we actually use the climate projections for? Well, we can use them for many things. As I mentioned before, people use them to study other planets. They use them to study the Earth in the distant past. We use them to do what we call attribution, which is determining why climate has changed in the recent past. And as you can see in this set of figures from the National Climate Assessment, the black line is our observed global temperature. And then we can use these climate models as our lab, and we can run a climate model with only volcanic eruptions, or only variability in solar output, or only greenhouse gas emissions from human activities, but nothing else. We can run these models with only one thing or only another thing, and then we can run them with everything all together, and you can see that that, at the bottom there, provides the best match. So we can use climate models for detection and attribution, but for our purposes, one of the most important things that we use them for is to look at the future. What the future will look like depending on what? Depending on our choices. So for example, as we go towards the middle and then the end of this century, what will our average annual temperature look like depending on whether we follow something closer to a lower scenario or something closer to a higher scenario? Climate models can answer these questions. And not only that, but we can downscale climate models to much higher resolution individual weather stations or fine scale grids, so that we can use this information not just to look at changes in variables like temperature and precipitation across broad areas, but we can actually look at what we expect to happen within the range of uncertainty, of course, for a given region, a given state, a given watershed, a given county, even a given city or town. And this is a lot of work that I do. So I've already referred you several times to Chapter 4 of the National Climate Assessment, and I would continue to refer you to it because it unpacks a lot of what I talk about in more detail. But in a nutshell, why do we need to downscale and translate, which we don't often talk about, why do we need to downscale and translate the output from global climate models? We need to do it for 2 reasons. First of all, the spatial and temporal scale of the output from the average global climate model is not what we need to look at a lot of impacts. Will a stream still be hospitable to fish? What is the range of an invasive or endangered species? How is the growing season going to change? That type of information we need both at a finer spatial scale and sometimes at a finer temporal scale, sometimes too, but we also need translated into something that we can use, like growing degree days, for example, or number of days above freezing, or number of dry days, or extreme precipitation frequency. So here on the right-hand side, you can see a figure that actually illustrates the difference between a global model output on the left and a downscale data set on the right. Not perfect, but still a lot better. How is downscaling done? There are 2 ways to do it. The first way is using a regional climate model. A regional climate model has the same physics as a global climate model, and it often has a little bit more because it gets down to a smaller scale. Remember, the global climate model might have a grid cell that's 100 by 100 kilometers, while a regional model might have a grid cell that's 10 by 10 kilometers. So it wouldn't have to parameterize as much as the global model. It could actually represent the physics directly. But global models can only be applied over a limited spatial area, like a rectangle, and they're also very time-consuming to run, as we'll see in a minute. So there's an alternative to that, which is to develop a statistical model. And the difference between this is sort of like an analog television versus a digital television. If you can get the digital one fine enough, it's good, but if you can't, then an analog is better. So people often say, well, which one is best? And my answer is it depends. It depends on what region you're looking at. It depends on what you're using this for, what your application is, and it also depends on your resources. Let me give you a couple of suggestions, or examples, I should say. So, regional climate models are physical models. They're not statistical models. They are physical models that they can actually simulate the physical processes and the topography for a given region at a much finer spatial scale than the GCM. They can often give you hourly or 3-hourly outputs as well. Some GCMs do, but not many, just because the data is so big, so they don't often save those files. But RCMs often do give 3 or 6 hourly outputs too. RCMs, regional climate models, also generate output from many variables at multiple levels in the atmosphere, so not just at the surface, but all the way up, and sometimes for soil levels too. They don't assume that the relationship between the GCM and the observations remains constant in the future, like the statistical models do, and you can use an RCM even where you don't have any observations. So for example, across the entire continent of Africa, they have about the same number of long-term weather stations as you do in a large, heavily populated state like Texas. So if you're working somewhere that doesn't have a lot of observations, a regional climate model has a huge advantage because it's based on physics, and it's nice to have observations so you can just, check the model to make sure it's not 100% off base, but you don't need the observations to actually generate the climate projections. On the other hand, statistical models, you downscale each variable separately. So you downscale temperature separately, then you downscale precipitation separately. Sometimes you can get some very complicated hybrid downscaling schemes. I've got a few of those myself, but they're purely experimental. We haven't published any results from them because they're very complex. In fact, often they might take as much time as running part of an RCM. So they don't maintain the physical connectivity between the variables, and they only generate output for the observed variable at the spatial scale of the observed variable. So in other words, if you don't have the variable, if you don't have the observations, you can't downscale to it using a statistical model. And they also assume that the relationship between the global climate model and the observations, which is basically the relationship between large-scale climate dynamics and fine-scale climate, we assume that that remains constant over time because the statistical model can't change in the future because you have no information to change it with. But on the other hand, at this point you might be saying, well, why shouldn't everybody use an RCM? RCMs are very computationally expensive, so they can only run a few GCMs in a few scenarios. On the other hand, statistical models are very computationally efficient. You can run, several tens of GCMs, 20, 30, 40 of them. You can run multiple scenarios. So if you really want to capture the full range of scientific uncertainty and scenario uncertainty, often an ESDM dataset will be able to do that for you, whereas an RCM dataset wouldn't. The other advantage of a statistical model is that it automatically, by definition, bias corrects the output. Remember how I mentioned earlier very briefly how because of the spatial scale of the model, there's always an offset between the output numbers coming out, like, average spring precipitation is 15.5 millimeters, a year. And the real precipitation is 14.2 millimeters per year on average. Well, that offset is primarily due to the fact that we're using parameterizations over large grid cells, whereas with a statistical model, because it's trained on the observations, it actually bias corrects it. So you will get 14.5 or 14.4, forget what I said, average centimeters of rain for that spring. Regional climate models, on the other hand, would still have to be bias corrected, so there's still an extra step. So if I had, unlimited resources to use, I would always use both. I would run a regional climate model for every single GCM we had for at least two scenarios, a higher and lower, and then I would use the statistical downscaling model to further downscale the regional climate model to finer scale observations. I would do both if I had the resources, but I've only ever had the resources once in my life, and I've been doing this for 20 years. So that's why most times, but not always, I tend to use a statistical model, because for me it's really important to capture that range of future projections and the scientific and the human uncertainty. But occasionally, if I'm working in a circumstance where, for example, as you can see in the yellow box, if I'm working in a region that does not have the observations that we need, or if I need a large set of complex variables like cloudiness, soil moisture, solar radiation, wind, in that case, I would absolutely use an RCM, because it would be more important to me to get all of those variables than it would be to get a range of GCMs and scenarios. On the other hand, if I'm working in an area that has a lot of observations and I want projections that exactly match those observations, like say I'm working with a city and a city uses 3 different weather stations in their planning, well, you can generate statistically downscaled projections for those 3 weather stations. So there's a 1-to-1 correspondence between the information they've already been using and the information you can provide for the future. And if what you want is you want temperature and precipitation, which you can easily downscale with a statistical model, sometimes you can even add humidity or solar radiation too. And you want it to cover a large range of scientific uncertainty and multiple scenarios to input into decision making. In that case, you would want to go with a statistical model. So there's no right answer to this. What the right answer is depends on you. It depends on your application, what you need, what you want, what is most important to you, and what resources you have. Now, when it comes to statistical models, there are many different kinds too. There's much more simple ones and much more complex ones. There is no best GCM, but with a statistical model, there can be better statistical models depending on your needs, because some that are less complicated don't resolve all parts of the distribution. They just don't. So it's not a physical uncertainty. It's not we don't understand the feedbacks in the system. It's just that it's like driving without your glasses on. You can see whether the light is red or green, at least I can, but I'm not going to be able to read the fine print on the sign. So some statistical models, you can see the color of the stoplight, but you can't read the text on the sign. And that might be okay if you only want to know if the stoplight's green or red. But if you want to be able to read the text on the sign, you have to use a statistical model that actually resolves that part of the distribution to give you that information. And it's not saying that the first model is bad, it's just saying that it's useful for a specific thing, right? So we have, with colleagues at the Geophysical Fluid Dynamics Lab, the GFDL, in Princeton, New Jersey, we've developed something that we call a perfect model framework. It's described in Keith Dixon's paper that he published in 2013, if you're interested. A perfect model framework where we can actually test how different statistical models how far they can see. In other words, can they see the green or the red light? Can they read the print on the sign? And what we're testing actually is we're testing the stationarity. We're testing what you lose by using a statistical model as opposed to a fully coupled dynamical model. Of course, the dynamical model is orders of magnitude more expensive, and it would be better to use that first and then use the statistical model after to remove the bias. But if you aren't able to do that, what do you lose by only using a statistical model? So this is how we design the experiment. We use a GCM that has been run at 25 kilometer resolution, which is incredibly high. And then we take that output and we coarsen it to a typical GCM, about 250 kilometers per side. We treat the high resolution GCM as observations, and we train the statistical downscaling models on the high resolution GCM in the historical period. So you got a trained statistical model, and then you give it the coarse future projections, just like you normally would. And then you get downscaled high-resolution future projections. But then you compare those with what you got from the 25-kilometer model for the future, because you only trained the model using the past. So you compare it with what you got from the future to see what information you lost by using a statistical model. Let me give you an example of what that looks like. So this is looking at the end of the century for 3 different statistical downscaling models under a higher scenario because we wanted to push this as far as we could. And this is looking at 3 different temperature variables. The one on the top row is the coldest day in 1,000 days. So that's a pretty extreme cold day, the coldest day in 1,000 days. The middle row is the 50th percentile, so the mean temperature. And the last row is the hottest day in 1,000 days. So that's pretty far to the other side of the extreme. And if there is no color on the map, it means that you get the same answer using the statistical model as you do using the fully coupled dynamical 25-kilometer model. Isn't that amazing? If there's blue on the map, it means that the downscaling model is too cool. If there's red, it means that it's too hot. And what you can see is that the delta method, which is the one that's used in the WorldClim data set, for example, that many ecologists use, the WorldClim method the delta method is extremely respectable if you're looking at average temperature, kind of in the middle of the distribution, and even if you're looking at places around the equator. I mean, even the subtropics, like most of the 48 states in the US, they look totally fine. But once you get up to Canada and the Arctic, the wheels fall off the bus. You are looking at biases in temperature on the order of 10 degrees Celsius. Yes, this is in Celsius, not Fahrenheit. So if you're looking at cold or hot temperatures in Canada or the Arctic, you definitely do not want to use the delta method. But if you're looking at average temperatures and if you're focusing on, Central Europe or the lower 48 states, then the delta method is a very simple method which is perfectly adequate. See what I mean? Then quantile mapping is the basis of the BCSD dataset and the BCCA dataset, which many people use and which was developed for streamflow modeling. And as you can see, for temperature, it does about the same as the delta approach. So it's actually more complicated than the delta approach, but it gets about the same result. Then the ARM method is a method that we developed about 10 years ago. It's a parametric quantile mapping method. And you can see that we do a lot better, except we have this really pesky bias around the coastlines. Because what's happening is the land is heating up more than the ocean. And so I suspect that the ocean breezes are getting stronger, driven by the temperature difference between land and ocean. And so that's actually cooling down the coast on the very hot days. But the statistical model doesn't have that in it, right? Only the dynamical model does. So that's why you see a bias on very hot days along the coastlines. What does this look like for precipitation? Well, here the story is different and it's very interesting. So here we're looking only at wet days. And we're looking at the 10th percentile, the 50th percentile, and the 90th percentile of wet days. So the 10% is the 10% wet days with the least precipitation, and 90% would be the 10% wettest days with the most precipitation, if that makes sense. What you can see is that the quantile mapping approach that was developed for stream flow forecasting and for hydrological modeling is absolutely brilliant for the 10th percentile, the 50th percentile, even the 90th percentile of wet days. It has the lowest bias of any method. So if you're primarily interested in hydrology, over time scales longer than about 2 weeks, the quantile mapping method is fantastic. The delta method, on the other hand, is really pretty bad. You can see that it actually has massive biases following the ocean currents. You can see kind of the El Nino region highlighted there. It is looking absolutely no good for precipitation except right up the middle of the North American continent maybe. But even there, it's got a dry bias. Now, stay with me here because we haven't looked at extreme precipitation, but we're about to. So far, we've gone up to the 90th percentile of the distribution, but now let's look at just a second here, let's look at the 99th percentile. So that is the wettest day out of 100 wet days, and the 99.9th percentile, which is the wettest day out of 1,000 wet days. And again, we took the not wet days already out. So it's not just the wettest day in 3 years, it's more the wettest day in 5 years or 10 years, depending on how much it rains in certain places. What do you see here? Well, you can see that for the hydrological method that's used in BCSD and BCCA on the right-hand side, the wheels really fall off the bus, and you're starting to look at a massive wet bias on the order of anywhere from starting about 20% up to 100%. On the other hand, the delta method is super dry. It's not dry by quite as much. I'm sorry, this is cut off a little bit here, but it looks like it's dry by about 20 to 40, maybe 50%. And the interesting thing is that the parametric quantile mapping method that is ARM, it has a greater bias, but the bias is more salt and pepper. It's brown and green. So it's not in one direction or the other, it's just noisier, which actually shows that it's not a systematic bias. So this type of information provides us with some guidance, not telling us what the best method is, but telling us that depending on our geographic location and depending on the variable and the time scale we're looking at, which method we could use. And I'm always in favor of using a simple method if it's adequate. The simpler the better. But if a simple method isn't adequate, this kind of analysis shows us why not and what we need to do to fix that. So now I just want to end with a teaser here because we are developing a brand new data set of station-based and gridded projections for all of North and Central America. We do not have gridded projections for Central America and the Caribbean or Northern Canada. We just have stations for those. But we do have gridded projections for the United States and for the southern half of Canada. And it is based on a brand new downscaling method that we developed actually using this perfect model approach. So we developed it within the perfect model approach, finding the places where we had the biases, figuring out the physical reason for those biases, and if possible, actually changing the statistical model so it accounted for those physical processes. So this is the figure I showed you before for temperature with the 3 different methods. And now I'm going to add to it a similar figure for this brand new method for this data set that we're releasing. Now, we already have temperature done for the weather stations. If anybody wants the raw .NET-CDF files, they're welcome to just shoot us an email. We can send you those if you're happy to process massive files like that. But we're also going to be making this data available via Esri, free of charge, so that people can download it in a much more friendly format, hopefully as early as this fall, 2020. Here is what the map looks like with the new method. It is not perfect. No statistical model is ever going to be, but there has been a massive improvement and a massive reduction in the bias. In fact, you have to reduce the scale of this figure to about plus or minus 4 degrees rather than plus or minus 10 degrees to actually start to see any significant bias. And where you see that bias actually is, interestingly, at the very tops of mountains, where it is specifically related to snow melt. Because snow starts melting earlier and earlier in the year as it gets warmer, and in the statistical model, it's not accounting for that. So we're actually thinking of starting to account for that because we know why it's happening. But that's why you see the bias up in the mountains. So in conclusion, this was a bit of a deep dive into downscaling, but I got a few questions after the original seminar, so I figured I'd go a little bit further with it. In conclusion, we are able to identify specific geographic locations and specific timescales or quantiles of the distribution over which you would or wouldn't want to use certain types of statistical models, but there's no one statistical model that's absolutely great and we should get rid of the rest of them, because all of them are useful, and frankly, the simpler the better sometimes, because we can actually understand what we're working with, right? I mean, one of the ones that we work with is thousands of lines of code long, and a delta method you could do in a simple, 5 lines of code. There is no perfect model, but there is a way to discover which statistical model is most appropriate for your application. And you can choose between a regional climate model versus a statistical model based on your needs and your capabilities.